We're now going to continue our coverage of Android and Java concurrency patterns by focusing on the command processor pattern. This pattern is a pattern that appears in several locations, starting initially in the so-called POSA 1 book, and then also being considered in a paper later called Command Revisited. And I'll provide links to all this information. It's also important to realize that the command processor pattern builds upon a pattern from the Gang of Four book called the command pattern that we'll also briefly touch upon. So what's the context in which this pattern gets applied in Android? So the challenge here is performing long duration operations. So if you perform long duration operations, things like downloading a large file or doing some kind of complicated database query or blocking on some kind of resource that may not be available immediately, then in those cases, if you do synchronous method calls, in other words, blocking method calls in the context of the Android user interface thread, these could block for an extended period of time. So for example, and we'll take a look at these types of examples later, if you want to do a two-way image download and you did it from the UI thread, the user interface thread on Android, that would block the user interface thread while the web server retrieves and transfers the image back down to the calling client on the device. Well, as you can imagine, this turns out to be a big problem in user interfaces in general, and specifically in the context of Android. And that's because Android will generate an application not responding, or a ANR dialog, if an app doesn't respond to user input within a short period of time, typically around 3 seconds or so. You can find out about these dreaded application not responding dialogues if you read the link at the bottom of the slide below. So therefore, if we end up calling the download image method in the context of the user interface thread, we're going to have problems. So what's the solution? Well, one solution, which is something that's very commonly applied in Android, is to apply the command processor pattern. And what this will do is it will actually download the image in a background thread, which can afford to block without disrupting the user interface thread or having the dreaded application not responding dialog pop up. And then we'll ultimately end up displaying the image in the user interface thread after it's been downloaded. Take a look at the link at the bottom of the slide for the paper called Command Revisited that talks about the command processor pattern in its modern form. The way this would work, to think about this in terms of how we would implement it in the context of Android using some Java mechanisms, we would start a background Java thread, which would perform this long duration download. And then we would go ahead and create a display image request using a runnable command object. And we'll talk more about this when we get into the details of this particular example. So we would create a runnable that would know how to display the image. And then we would pass that runnable from the background thread where it was downloaded, blocking, to the user interface thread, where it will ultimately be displayed without blocking, or at least not blocking for very long, however long it takes to put the image up and display it in the user interface screen. So what will happen here is that we're going to use something called the Android Hammer framework, which stands for handlers, messages, and runnables. And this will end up being used to pass the runnable from the background thread to the UI thread, the user interface thread, where the user interface thread will then go ahead and dispatch the run hook method on the display image runnable so that the image will be displayed in the context of the user interface thread, even though it was actually downloaded in the background. So let's talk a bit about the command processor pattern, the way it would be described in its various incarnations, starting in the POSA 1 book, Pattern-Oriented Software Architecture, Volume 1 book. So the intent of this pattern is to package a piece of application functionality, as well as parameterizing it in an object form so it can be usable in another context. So other contexts would be a later point in time. For example, if you do some kind of deferred queuing model in a different process, which would be the case if you were trying to run these things in, say, a distributed system or a cluster-based environment, or in a different thread, which is how we're using it in this particular use case for downloading and displaying an image in the context of an Android app. The Gang of Four book has a similar description for a pattern called the command pattern. And this pattern is quite a bit like the command processor pattern, but the main difference is that the command pattern doesn't really talk about doing things in multiple threads or multiple processes. It really talks about packaging up capability in the form of an object and then passing it around. But it's not really dealing with the concurrency part, whereas command processor is really focusing more on concurrency. So when should you apply the command processor pattern? Well, as is often the case with all these patterns, it's when you need to decouple something. And in this case, we're trying to decouple the decision about what piece of code should be executed or run, like our runnable command, from the decision about when and where this command or this executable should be run. So as we talked about before, you can specify these objects as commands. You can queue them up to run them later. You can execute these requests on a component in another process, in another thread at a different time, or these other processing contexts. You also could use this pattern when you need to ensure that enhancements to the services that are offered by a component don't break existing code. Again, because we're decoupling the client, the thing that's creating the request, from where the actual request is run. We can have a nice abstraction barrier to make it easier to make changes without breaking existing stuff. Another motivation for applying this pattern is when additional capabilities should be implemented consistently for all requests to a service. So we want to be able to have a single point where we plug in these new capabilities. Examples of these kinds of capabilities would include things like undo and redo operations, as well as the need for persistence. The Gang of Four command pattern, of course, talks quite a bit about the ability to do undo and redo operations of commands. So now that you have a bit of an understanding of the intent and the applicability of the command processor pattern, let's take a look at the structure of how it works. So here's the structure diagram along with the participants that are typically involved in this pattern. As is always the case, we'll first kind of talk about the participants or the roles in the context of the pattern that you would find if you read the Post 1 book, and then we'll talk about how this maps onto our example. So we'll start out first looking at the command. So the command is going to be an interface or a superclass that has an execute method on it. So it's basically a functional interface. In our context, in the example we're using here, which is the image downloading example from Android, that would be the runnable interface with a run method. Then we have something we call the concrete command, which implements or extends command, and it would provide additional parameters, and it would fill in whatever execute is going to do. And in our case, this would be the display image runnable object that we were talking about that would actually be passed from a background thread to the user interface thread to display the image after it's been downloaded. There's also a role or participant called the creator, and that's what's used basically as a factory that will create the command. In our case, that would be something called download runnable, which is an object that is going to create the appropriate command. And the creator will pass the created command to the executor, which will actually do the work to run it. And in our case, the example in Android, the executor will be the Hammer framework, the handlers, messages, and runnable framework that Android provides to be able to pass runnables from a background thread to run in the user interface thread. And then the final piece of the puzzle here is what we call the execution context. That's where the command is executed. And in our particular case, that would actually be the download image activity, which, if you're familiar with Android, is something that's going to run in the context of the user interface thread and actually interact with the user, in this case, by displaying the downloaded image. So now that we've talked a bit about the structure of the command processor pattern, let's talk somewhat about its dynamics. In other words, how do different pieces talk to each other and call each other? So here's a diagram that illustrates this. As you can see, the creator would create a runnable and a thread and call start on the thread. And then that would allow the thread to run in the background. And keep in mind, we have the executor framework, which is going to be the Hammer framework. That's the thing that's actually going to run the requests that are sent to it. The execution context will end up being the part of the code that will call the run hook method on the runnable created in the background thread in order to be able to take the image that's been downloaded in the background and then display it in the context of the activity. And of course, the concrete command here would be the thing that we would use in order to be able to pass the downloaded image from the background thread to the execution context, which in this case would be the user interface thread. So what are some of the pros and cons of applying the command processor pattern? Well, one of the really nice things about this pattern is it allows us to be able to have context and time-independent execution of the application logic. In particular, this allows the command to execute in a different thread or after time elapses, or if we're going to be using it in a broader distributed environment or network computing environment in a different process running on a different machine. We don't have that particular use case here in our Android example, but it's a very common use case for the command processor pattern. So you can see here is just a little bit of snippet of code. This is code that would run in the display image activity, which would be the user-facing portion of Android. And you can see here that on the on download operation, what it's going to do is it's going to have this runnable that's created with a run hook method. And this run hook method is going to be used to actually take the bitmap that's been downloaded and then display it in the user interface thread. So that's going to run in the user interface thread. Another nice property about this pattern is that the client doesn't need to block for the duration of the command processing. So the client, which in this case is actually the background thread, the thing that's going to call the run on UI thread mechanism, that is going to go ahead and it's going to run in the background, download the image, and then pass the image over, downloaded image. It's going to pass that over to the user interface thread by making an API call that's provided by Android and its Hammer framework. But the client, which is the caller, in this case, the background thread, doesn't have to block while that's taking place. And the way that this works is the background thread is going to end up calling the run on UI thread, and the run on UI thread is then going to take the image that was created and it'll display it in the context of the user interface thread. Basically, this approach can be used to emulate closures in object-oriented languages that don't natively support this feature. You can read more about what a closure is here at this link. It's basically a way of creating an object that encapsulates a method in any state it may need, and you can pass these closures around as kind of as first-class objects in the type system. So we can use the command processor pattern to get us closer to closure-like semantics in a language like Java that doesn't really have first-class support for closures. Although with later versions of Java, especially with modern Java, Java 8 and beyond, with Lambda expressions and so on, Java gets pretty darn close to supporting first-class closures. So you can see here, what we're going to do is we're going to have a method together with its referencing environment. This is what's going to make the closure. So the referencing environment here is going to be things like the image view and the bitmap that we're going to be able to display after downloading it in the background. Naturally, not everything is unicorns and rainbows when it comes to any given pattern. So one of the downsides of potential cons of this pattern is that the functionality is driven by the sender of the command rather than by the receiver. So it's the sender that decides what will be executed in the different context. And that should be compared and contrasted with the active object pattern, which is another pattern from the POSA book series, the POSA 2 book series in this case, which we'll talk about in a later video, where the receiver decides what to do the processing rather than having the sender do it. So as you can see here, the user interface thread, which is the receiver of the command sent to it by the background thread, has little or no control over what function is run. It's whatever it's told to do. So that's what it does. Another potential limitation with this pattern is it's really primarily good for one-way operations. And if you want to do two-way operations where you send something and get a response back, you have to do some additional programming effort if you want to be able to return to sender with our Elvis Presley stamp metaphor here, or meme. So two-way communication is harder with this type of an approach. Let's briefly summarize some of the common known uses of the command processor pattern. This is a very, very common pattern. A lot of user interface toolkits use the command variant of this. They don't necessarily run computations in the background thread in some of the earlier user interfaces, but the modern ones do. Modern ones like Android or Swing and so on. You also see things like the Java runnable interface that's used by Java's threading and executor framework being very commonly used to execute commands and using the command processor pattern. In fact, you can think about executor service in Java as being a great example of passing commands around, which are basically runnables or callables. Our focus here has been on the Android Hammer framework, where you pass a runnable from a background thread to be run in the user interface thread. And then there's also something else called the Android Intent Service, which is really intended more for sort of multi-process communication or inter-process communication, where you send intent objects from one process, typically a user-facing process, a user interface activity process on an Android device, to a background process running on that device, which will then process the intent and then do something, and perhaps do something in response to that. That's another classic example of the command processor pattern. So to summarize this part one discussion of the command processor pattern, this pattern provides a relatively straightforward means for passing commands asynchronously between threads and/or processes in concurrent and network software. Our focus here, of course, has been primarily on passing the commands asynchronously between threads, but be aware this generalizes to inter-process and inter-machine communication. The nice thing about this is requests and responses don't need to proceed in lockstep. They don't have to go, request, response. You can do request, response, response. So it gives you more flexibility if you need two-way communications at all, of course. The command processor, as you can see here in the diagram from the POSA book, it acts as a manager for the functionality of a component. So its job is basically to take these requests that come to it from clients or a client and then get them sent to the appropriate context to execute the request, which could be a thread or a pool of threads or a pool of processes on the same machine or on different machines. So the nice thing about this is that the component client doesn't care what's happening. It just knows that things are getting executed in the right environment. So again, as one of the key consequences here, you have nice loose coupling between the various parties, between the client and the server, or the client and the service implementation. And that decoupling makes it easier to write software that can evolve and change without having everything have to proceed as tightly coupled and in lockstep as would otherwise be the case. Take a look again at the link at the bottom of the slide for more information on the revised version of the command pattern that's a little closer to what I think most of us would come to recognize as modern uses of this particular pattern.